Matt, Federico, Raphael, and Sunny are going to make a presentation on automatic wireless quality control with a company that they call intelqual. Okay, one of the things that I wanted to tell you, their business proposal is in this particular file. So there is a proposal that says intelqual on the, and that is their business proposal, right? Okay.
Good afternoon. My name is Raphael. Raphael Wilches and Sunny Patel. I'm going to be presenting our project, intelqual. It's automated wireless quality control for RF devices. Our objective is to create an integrated system in the assembly line. We will be able to increase overall quality by boosting the number of tested units that a manufacturer can have in their quality control process. We want to provide accurate and rapid quality control and problem identification. This will increase efficiency, improve quality, and create an outstanding reputation and increase market share for companies in a crowded market. And one key goal of our project was to allow room for upgrade and expansion in the future. Current quality control methods are largely, they're offline and they're disruptive, meaning that the manufacturer has to take the device off of the production line to test it. They have obsolete equipment and laggard management that leads to poor product quality. So right now in the industry, there is a great need for automation and systemization, and that is what our company is driving at. Our approach is two-tone RF probing. We generate two frequency-stepped RF signals, transmit them via an antenna at the device. The two tones enter the device, and inside they encounter nonlinear junctions, amplifiers, diodes, mixers, and there generates intermodulation distortion. And these signals are re-radiated by the device, and each device re-radiates a unique signal that constitutes a signature. This approach has been applied by others. For example, these two gentlemen from Purdue University applied it to characterizing devices that are violating FCC regulations. Our approach is to apply the similar technique for quality control purposes. As I mentioned, right now, quality control is typically offline in artificial testing, where they rely on small samples and they use statistical data to arrive at their numbers. This is a very slow, time-consuming, laborious, and costly process, and that's what we are aiming to solve with our project. There is automated test equipment out there, mainly used by large defense contractors such as Lockheed Martin, but these are very expensive, they're very specific, and they're prohibitively expensive for our target market, which is smaller manufacturers.
Now, our first goal will be to characterize the device under test by applying this two-tone RF probing technique. Once we achieve this capability, we'll be able to train our system. The training of our system will develop a catalog of device signatures which fall under two categories: those devices that are known to be operational and those that are known to have a specified defect. Given an unknown device whose condition is unknown, we can then compare its signature to those in our catalog and designate it a pass or fail, and if there is indeed a fail, we can identify what the particular defects were.
This is a functional block diagram of our system. As you can see, it's divided into two blocks. One is the transmit and the other is the receive. On the transmit side is generally, it's responsible for generating the signals, the probe signals according to our specifications, and radiating them at the device. Once the signals come out of the device, they get to the receive chain, where we process the data, we make the comparison with the signature data, and the end result is the classification of the device. This is our first initial setup, experimental. It's wired. This will eliminate some of the problems that are associated with wireless testing. We'll use 50 ohm coaxial cable for transmission. We have the two signals from the generators combined in a combiner. They go through a circulator which isolates the transmit and receive signals. The signals that come out of the device then go to a spectrum analyzer where we collect the data, and then it goes on for processing. Then we will replace the coaxial cable with a wireless channel. We'll have 2 transmit antennas and 1 receive antenna. And this, we will then have to reevaluate the device responses and collect signatures. In this setup, it'll be important to find the optimal antenna geometry and output power that will optimize our performance. We've identified a test device for this phase of the project. It's a Graymark 542 AM/FM radio. It provides a very simple electronic circuit. It comes in a kit with a schematic diagram so that we can easily identify the specific defects that we're aiming at finding. And again, it provides a very simple circuit that we can easily understand and characterize. Some of the specifications that we've identified for the transmit side, obviously we want to cover the transmit band of our device from about 500 kilohertz up to 150 megahertz, the AM/FM radio bands. We need significant power to elicit a response, and linearity is important, as well as isolation of the transmit signals, because we don't want to be transmitting intermodulation distortion that's generated in our signal generators and amplifiers, which is because we want to measure only the intermodulation that occurs in the device. On the receive side, we need significant signal-to-noise ratio, at least 20 dB, to be able to extract the signatures from the device. And we require a digital spectrum analyzer with a sufficient sample rate of about 500 megahertz, memory storage capabilities, and a narrow enough resolution bandwidth.
Now, we've identified 4 classification algorithms for use in our prototype. Our preliminary research suggests that the k-nearest neighbor algorithm is the most promising. The basic principle of this algorithm is to estimate the distance between the test vector and the training vector, and that way make a comparison. The way in which we'll be doing our performance evaluation will be testing 100 units. Our aim is to achieve a 2% error rate in pass and fail designation and a 5% error rate in defect identification. These are some of the key milestones we've identified. Perhaps the most important is the detection of the first device failure for the algorithm, as this will determine proof of concept. Once we've achieved this, we can focus on meeting our specifications and performance metrics. This is how we distributed the task amongst our team members. We've done this based on their strengths, not only derived from theory, but also from practical experience. If we start from counterclockwise direction in the upper right corner, we have software, hardware, systems, and management and organization. Now, the following is a Gantt chart, which we'll be using to evaluate our performance, our adherence to a schedule. And as this is a living document, there will be changes made as we encounter problems. Now, this concludes the technical overview of our product, and we'd like to turn over the presentation to Rafael Wilches and Sunny Patel, who will discuss the business aspect.
Thank you. I will be going over the business part and the marketing along with Sunny Patel. Just as a brief overview, I'll be mentioning the executive summary, some of the challenges that we face, the marketing, and the cash flow. intelqual is a service-based business that provides quality control solutions to AM/FM radio manufacturers in China. Some of the challenges that we face are recognition, building profits, and providing suitable prices. The main goal of the company is to become recognized through excellence and innovation, and to target 5% of the total market within the first 5 years, and eventually to expand into other wireless industries. This is the market potential. As you can see, just in Hong Kong and China, 97% of the manufacturing of AM/FM radio is done. That's why we intend to pursue our marketing and market in China. As my fellow Matt and Federico had mentioned before, the current processes are very costly and obsolete. That's why we've turned this innovative product, which is intelqual, to provide high quality at low prices. Some of the strengths that we have is is the technology that we are bringing in has not been implemented in the production line. We are service-based, which gives us an advantage in getting contracts and keeping cash flowing for long periods of time. One of the main weaknesses is that we don't have a brand for our name, and so we'll need to get recognized through our marketing strategies. Some of the risks that we face is the rapid loss of equipment due to malfunctioning, also the equipment theft, theft of the intellectual property, and we plan to combat these risks by ensuring our equipment, maintaining strong customer relations to prevent loss of contracts or loss of sales, and to patent our current processes and future processes used. I'm going to hand it to Matt to talk about the manufacturing plan.
The first part of our manufacturing plan would be, after we've identified a customer, is to send a team of engineers to their site to survey their site, identify their needs, see what kind of devices they're working with. Then we'll begin to order OEM parts. We're going to mainly order parts from other manufacturers, at least in the beginning. National Instruments for signal generation, other things for test enclosure, UTS, Lindgren. And then we're going to begin to program the transmit signals based on their equipment and their specifications and what they need. Then we will train the system. Again, as mentioned before, we'll train the system, develop signatures, and then we'll program a very customer-specific classification algorithm based on what they want as far as error rates and what kind of problem identification that they need. After final in-house testing, we'll go to the customer site where we'll have engineers who will integrate it into their assembly line with minimal loss to their productivity as fast as possible, and then we'll be able to turn the system over to them where they can begin to utilize it for their benefit. And Sunny Patel is going to finish up the rest of the business proposal.
Good afternoon. As you can see, as venture capitalists, we have a need. I would like to propose two things to you: pricing and marketing. Pricing, we see an inflow with two ways, whether it's equipment-based or service-based. Primarily, our main source of income will be through its services that it provides. Equipment, we're going to be leasing it out to the manufacturers, and the ability for us to create an inflow of cash will be through our ability to service them through our research and development and upgrading the system itself. Marketing, we see ourselves targeting these manufacturers through primarily relationship selling. We want to be able to create a bond with them. What we see in the first year, we'll see that there's very few competitors in the market. So this is the time where we form relationships with the clients and the manufacturers, make sure we have them on our sides, that their needs are being met, whether it's towards quality control or whether they need a better margin of error for the system. And so it's very important that we keep our marketing up the first year. As you will see, I'll talk about it later on towards our advertising and whatnot. But this is the first year's cash flow. As you can see, the first year we're primarily targeting these companies or manufacturers in part to make sure we get our brand name out. We want to be able to break the market barriers, and in order to do that, in the introduction of the phase in our product, we have to advertise immensely. That's why you can see a increase of about $300,000 of investments expense towards advertising. As you can see from the cash flow, there's $6 million, which we'll be investing over the 5-year term. In the first year, we expect our net expense to be about $1.544 million. Go into the 2-year comparative income statement, you can see a significant increase. As you can see, the expenditures for year 1 is 1.55 as a minus, as a deficit. But in year 2, you see a clear-cut profit of being made of $394,000. This is mainly due to the revenues that we'll be bringing in from our year 1, where we've targeted a lot of these companies and went through advertising. As you can see, the advertising in year 1 is $300,000. We've realized that in year 2, we should have a fair enough amount of the market where we can lower our expenditures, not drastically, but over a period of time, where it's important to make sure we advertise, but it's also important that we're upgrading our products, so that investment will be going into research and development of other services that we'll be providing over the years. The profit and loss statement for the five-year plan looks promising. As you can see through this chart, year one is our deficit, where we're going to see a great deal of losses. So over the 5 years, we're going to be trying to break through, making a positive cash flow. And year four, you can see that after all the incurred debt, we'll be breaking about even, actually making a profit in year four due to our continued gross revenues increasing steadily. And as you can also notice over here, as the cycle goes on for 5 years, the advertising cost varies. Year one, we expect to be introducing our product. It's heavily going to be marketing. It's going to be heavily marketed. Year 2 and 3, we're going to decrease our marketing plan, where we're going to focus on our clients, manufacturers. Year 4 and 5, we see competition coming into the market, eating up our share. That's where we want to start steadily increasing our advertising, showing them our new research and development products and services. And our exit strategy is to either merge with one of the top leading companies, Motorola, L3 Communications, or Nokia. We feel that we'll hedge our risk from the cash flow and be able to capitalize on the market within China. And as you can see, Motorola hopefully is our target company, because they're primarily focusing on radios, as they always have. We would like to acknowledge a special thank you to Dr. Dewan, Dr. Niver, Dr. Kirchhoff, Dr. Passaruni, Dr. Pasonic, Mai Young, Leon Baptiste, and Don Blackman. Thank you for sharing the wealth of knowledge. You guys have been grateful and helped the department tremendously, and we would like to really thank you for helping us out during the course of the semester. Thank you.